All right, everyone. So a roadmap to the end of the semester. Excuse me. So we've got exam on Friday, exam 3, energy balances. Okay? So this could be closed systems, open systems, reacting, non-reacting, phase transitions, using steam tables, not using steam tables, right? So all of that. So don't expect a tremendous amount of material balances. So a lot of the material balances may be taken care of for you. There still may be some material balances, right? So I could still ask you to balance a flash calculation and then figure out the energy hypothetically, right? But all of this is going to be necessary preparation for the final exam. So many of you may not be super thrilled with your exam 1 or 2 or maybe even exam 3 performance, right? But not all hope is lost, okay? So if you did not as well as you had hoped for on one of the exams, the final, so for example on exam 1, section 1 of the final will be like, 7, 8, 10 questions, but really short, straight to the point, multiple choice style almost questions, right? So if you get 10 out of 10 on that section, 100%, I will take that 100 and you still get that on the final, right? That all contributes to your final exam score. Then I'll take that 100 and I will average it with your first score. So let's say you got a 90 on exam 1, right? And you get 100 on the final. You only get 5 extra points, right? And that gets added to your exam 1. Let's say you got 10, right, on the first exam. That means I will average 10 and 100, which is going to be 55. So you would get 45 extra points. Okay? So your score can completely transform by the final exam. So make sure that you are understanding all the content extremely well. So I thought of a good analogy that may be helpful for these types of questions. So if you're learning a musical instrument, and they say, well, how long do I have to practice for, right? And you could practice until you get it right, or you can practice it until you cannot get it wrong. For this class, I would recommend that you practice the homework, practice the prior exams until you can't get it wrong. So that means if you're saying, hey, how do I prepare for this exam, like exam 3? Well, if the homework says use the heat of formation method to solve the problem, well, maybe you should resolve it using the heat of reaction method. Maybe it would be beneficial to write out the whole energy balance symbolically with algebra and then confirm that the methods are identical. Let's say you do an energy balance on a flash calculator and you're lazy, right? And you just use Watson's correlation, right? You don't want to do this whole heating up with the liquid and cooling down with the vapor, right? So maybe resolve the problem, but instead of using Watson's correlation, you use a different approach to estimate the heat of vaporization. Let's say we have an energy balance, and you say, I'm going to assume that the inlet stream is the reference state. Well, what if you chose an arbitrary reference state? Let's say 0 degrees Celsius liquid water, right? Resolve the whole problem and see that you're getting the right answer for each of the different approaches. Then when it comes to the exam, you may not necessarily be able to use Watson's correlation. Maybe you have to solve it a different way, right? So having the multiple different pathways to solve each of these problems is going to be advantageous because you will have the skills and the proficiency to work on each of them. Same thing with balances. Let's say you solve it one way with an atom balance, solve the next way with the molecule balance, then solve it with the extent of reaction. You should be able to get the same answer on all of them, right? So just because the particular homework problem or the particular exam or the particular solution has it being solved one way, that doesn't mean that you can't on your own independently work through it a different strategy. Does that all kind of make sense? If you feel comfortable solving most of the problems in any arbitrary way, you should have no concerns about the final whatsoever, right? So the preparation now is to convince yourself and force yourself to be able to solve it. So if you approach a particular problem and say, I only feel comfortable with the heat of formation method, I don't feel comfortable with the heat of reaction method, right? that's an indication that you are not necessarily as confident as you would like to be for that section of the content, right? So when I prepare for a class, I have to try to anticipate what types of questions there will be. So at every single step along the way in the example, I try and think of, okay, what could a possible question be? How would I respond to it? What would a possible question be and how would I respond to it, right? So then basically what I'm asking you to try and do is become your own instructors. And the tools that I use to make sure that I know what the hell I'm talking about is I resolve the problem a bunch of different ways. Or if I'm using a non-ideal equation of state to solve a problem, I'll double check my work with an ideal equation of state to see if it's on the same order of magnitude. And I'm like, okay, it's close enough, right? So these are all the strategies that I will use to teach myself the content before I teach it to other people. So Wednesday, we're going to do a review. Today, we're going to talk a little bit more about reaction balances, and that's the end of reaction balances. It's the end of energy balances. Friday is going to be the exam. Monday next week, I'm planning on doing a day devoted to just project help. Right? So in class, come with your computer, come with your work. Let's talk through the project. I will give you as much assistance as I can to make sure that everyone can build their computer code or spreadsheets that allows them to balance the entire process. All right? Wednesday, Friday, and Monday, next week and then the following, 2 weeks from today, those are our last 3 lectures. Those are going to be divided up between transient system balances. So you know how we've always neglected that dm dt or du dt? We're not going to neglect it then. And we're going to talk about how that transitions into your junior level classes. But we can also spend some time talking about part 2 of the project, which is going to be the energy balances. But I assure you, if you build your spreadsheets in an organized fashion, the energy balances are not too difficult. You could use the heat of formation method for processes that don't even require reactions, right? You can choose an arbitrary reference point and you can just build your entire energy balance calculations from a single standard reference point, right? And then you just add up the enthalpies in, subtract the enthalpies out, and you're good to go. Or depending on how you build your energy balance, maybe it's out minus in, right? All right, any questions about the last 2 weeks of class? Yes?
In the exam, will it mainly just be heat-focused energy analysis, or could we expect something like a compressor or a turbine or something?
Could very well include PV stuff. So for example, I think there's a question on the practice exam, which I posted, about the energy it takes to inflate like 1,000 balloons. I think the question is, how many bananas do you have to eat in order to inflate 1,000 balloons? So yes, that'd be exactly the question that you were asking. Okay. So the lecture today is going to transition into transient balances and some of the concepts that you're going to be covering in your junior year. So we had a question last week about, hey, what if we don't know the molecular formula of the fuel, right? Because that's what we talked about a lot in combustion. We look at the atomic composition of the fuel, and we don't actually care what the molecules are. And that gets lumped into something called the heating value. So for something simple like methane, we know what methane's chemical formula is. When we purchase natural gas, we know it's mostly methane. There could be some ethane or ethylenes of trace amount, but it's mostly going to be methane. There's 2 terms that we want to consider here. One is called the higher heating value, and this is abbreviated HHV. This is going to be equal to the negative delta H of combustion at the standard state. So the heat of combustion, right, is the delta H change in enthalpy going from your fuel to your CO2 and H2O. Now, if it's any sort of a good fuel, that should be a really negative number, right, because you want those fuels to burn very exothermically. Otherwise, it's not really going to heat your house, right, or heat your chemical process. So the higher heating value is just the negative of the delta H of combustion, just so you get a number that's positive, so it tells you how much energy you get out. So basically, it's just changing what you consider good energy, right, coming out of the system, or useful energy. So this means that in the higher heating value, you get liquid water at 25 degrees C out of the process. Now, I don't know about you, but whenever I burn something, I very rarely cool down the combustion gases, condense the water, and say, now I've extracted all the energy from that, right? But the higher heating value is an indication of how much energy it's going to be. So for something like methane, this could be in kilojoules per mole. But what if I'm burning coal? I'm not necessarily going to know what the molecular formula is because there's going to be millions and billions and trillions of different molecular formulas. So my higher heating value is potentially going to be in some sort of megajoules per kilogram. So that tells you if you burn this fuel, you cool the product outlet to 25 degrees C, you condense all the water, that's how much energy you'll extract out of that fuel. So when you're purchasing coal A versus coal B, or liquid fuel 1 versus liquid fuel 2, what you'll basically want to be looking at is how much energy am I going to get out per gallon, per kilogram, what's the cost per kilogram, what's the cost per gallon, and then you balance all that out. If one has a high sulfur content, you're going to want to purchase it at a cheaper rate because then you're going to have to scrub the SO2 that comes off so you don't sort of produce SOx to the atmosphere that creates acid rain, so you're limited in the amount of sulfur emissions. So sulfur-rich fuels are going to be sold at a discount, so you'll get more energy and you can work that way. So an interesting thing that's happening right now in the refinery industry is the United States is one of the world's largest oil producers right now, but we still import a tremendous amount of oil. Does anyone know why we import a lot of oil even though we produce a ton of it? Back here.
Is it because the oil that we have is kind of hard to extract because it's a bit like shale and sand as opposed to like
It is very hard to extract, but we figured out lots of good ways, not lots of good. We're okay at extracting it. The thing is there's lots of oil in those shales, but we're only actually getting like 10% of it out of any given reservoir. So we're very bad at extracting all of it. But that shale oil is very, very good. Okay, Miles.
Export in oil, right? We produce a lot, but export a lot, and we import a lot.
Correct.
Is that because bureaucracy?
We're a net exporter now, though. But why? So why do we still import oil?
Because bureaucracy is inefficient.
It is, partly, but there's other reasons. Thomas.
Don't we import a bunch of cheap unrefined oil and refine it here, and then we export the higher quality?
Of sorts, yes, and then fine. Same thing. Okay. So before about 2010, 2012 or something like that, we didn't produce a lot of the shale oil. So this has been a pretty big revolution. So what we end up doing is we produce this shale oil now, but all of the refineries that we have in the United States are designed to take in really heavy sulfur-rich oil from a lot of different places. So for example, Venezuela characteristically has really heavy sulfur-rich fuels. So all of our refineries are set up to take heavy sulfur-rich fuels, and those actually have the highest profit margin because the technologies to remove the sulfur to turn it into, let's say, for example, ultra-low sulfur gasoline or diesel are very expensive and complicated technologies. So we can buy the oil much cheaper, even though it's being imported from across the globe, we can still make more money because we have better technologies to remove that sulfur. So countries that don't have as advanced of refining technologies as we do, we sell that nice, beautiful shale oil that we take out of the ground from fracking and we give it to someone else who doesn't have the same advanced technologies to remove all that sulfur. The profit margin on that is a little bit lower. So that's kind of the weird system we have. And the other complications, which is related to my research, is that you can't actually mix heavy and light crude oils together because they'll phase separate from one another. And that causes all sorts of gunking up and problems. So the real world is very complicated, and the decisions of why we make things certain ways is not just one simple fact. There's a lot of confounding issues. Okay. So the higher heating value gives us an estimate of how much energy we're going to get out of something when we burn it. There's also something called the lower heating value. And this is where we have, so it's LLV, this is where the outlet is vapor H2O at 25 degrees C. Still not exactly what we would expect to have in a fuel being burnt, right? but it's a more realistic scenario for how much energy you're going to get out of it. Question?
Is it supposed to be LLV or LHV?
Oh, LHV, yes. LHV. So the difference between these two is that the higher heating value is equal to the lower heating value plus the number of moles times by the heat of vaporization of water at 25 degrees Celsius. Or correspondingly, the lower heating value is the higher heating value minus the number of moles of water you produce times by its heat of vaporization. So the difference between these two is just the energy of vaporizing the water or condensing the water. And the heat of vaporization of water at 25 degrees C is 44.0 kilojoules per mole. This is not the number you'll notice when you look up the heat of vaporization of water, because that's generally at 100 degrees C if you look it up. But this number here is the difference between, let's say, the heat of formation of water in the liquid state versus the heat of formation of water in the vapor state. They will differ by 44 kilojoules per mole, because you can make water as a liquid, and then you can vaporize it, and that takes the 44 kilojoules of energy, and that's the difference between those two heats of formation. So anytime in the back of the book you see two heats of formation, it'll tell you, is this for making the gas? Is this for making the liquid? So if you wanted to be clever, that difference is the heat of vaporization of that fluid at 25 degrees C. Okay? So I'll just put down methane right here, because this will be relevant to our example that we'll work through here quickly. So CH4 plus 2O2 goes to CO2 plus H2O. Right? The reason why methane is sort of the quote-unquote cleaner fuel compared to a lot of other fossil fuel products is because for one methane you only get one CO2. A lot of fuels like coal or heavy oil, their carbon to hydrogen ratio is going to be closer to 1 to 1. So for every one carbon, you get one hydrogen. Methane has one carbon to 4 hydrogens. Right? Hydrogen is the clean burning fuel. If we burn hydrogen, we only get water. So that's why methane is nice, because you get 4 hydrogens being burned into 2 waters, and only 1 carbon to 1 CO2. Right, so that's why everyone was protesting pipelines for the Canadian oil sands, is because those are much heavier, so they have a much lower carbon to hydrogen ratio, so a lot more carbon in them, which means that per kilojoule or megajoule of energy, you have to produce a lot more CO2. So methane is good because we get a lot of energy for not a lot of CO2. So if we look at the heat of combustion, the delta H of combustion for this process is minus 890.4 kilojoules per mole. That would mean that the higher heating value is 890.4 kilojoules per mole. The lower heating value is going to be the higher heating value minus the number of moles of H2O multiplied by its heat of vaporization. So that's going to be about minus 88, because we have 2 waters that we're going to be condensing or vaporizing. One sec, I'll get to your question in a second. It's 802.4 kilojoules per mole. Question, Miles?
So, if we know the exact difference between HHV and LHV, why do we have the 2 different measurements?
Conventions. Just easy. Engineers are lazy. The fewer the calculations you have to do, the better, if it's easier to look up a number. And different organizations may have different preferences of how they do it. 890, both of them. Okay, question?
Does that say H2O next to the N?
Yeah, it's the number of moles of water that's being formed, because the CO2 is not going to be condensing to a liquid at 25 degrees C. So it's only the...
We reference the water for that?
Was that?
We only reference the water?
Correct.
Okay, so N.
Right, so for example, the heat of combustion and the higher heating value, The CO2 and the water, they're both at 25 degrees C in 1 atmosphere, right? But I can't condense CO2 to a liquid at 25 degrees C. I can only condense the water. Okay. So
So N in the upper formula, HHV, LHC is less N.
this is NH2O as well, yeah.
Okay.
H2O. It's the number of moles of water.
Formed or
What?
is that H2O formed or H2O?
H2O formed. Yep. Because we're only manipulating the products here. Okay. So we talked a little bit on Friday about an adiabatic reactor. This changes nothing from our energy balance. It changes nothing from whether we use the heat of formation versus the heat of reaction method, right? Doesn't change a single thing. The only thing that is different is that in an adiabatic reactor, we are generally going to set Q, well, not generally, we are always going to set Q to equal to 0. But we will generally be solving for the outlet temperature. Not 100% true. You could also do an adiabatic process where you're solving for the inlet temperature. And I don't recall if it was on exam 2 or the practice exam 2. There was a question about trying to dry a slurry. I think it was the practice exam 2. You were trying to dry a slurry with hot air, and you wanted the process to be adiabatic, but you needed to vaporize a certain amount of water, right? And so then you were trying to figure out what the inlet temperature of that water was, right? I believe that was the case. Or maybe that's...
I think it was on the actual exam.
That was on the actual exam? Was that a homework? Well, one of the ones. You guys had a question like that. But anyway, in that case, you were solving for T in, but it was still an adiabatic reactor, right? That's my point. So if you don't have any heat going in and out, you're manipulating the temperatures or the flow rates or something associated, not with the heat, right? Okay. So we're going to calculate what is the adiabatic flame temperature of burning methane. So how hot does methane burn with oxygen with no heat going in or out? So that basically means that all of the energy being released in the heat of combustion doesn't get removed from the system. It only goes into heating up the reactants and products. Okay? So I'm going to use the heat of reaction method. Okay, and this is a good scenario where it's not too bad to actually do the heat of reaction method. So I'm going to have 1 CH4, 2 O2, reacting to form 1 CO2 and 2 H2O. And I'm going to make this vapor because this is going to be a very high temperature. So I'm pretty confident the water is going to be a vapor. So in this case, the delta H of the reaction is going to be equal to the negative lower heating value. The higher heating value, or the delta H of combustion here, that would be for liquid water as the product. So I'm going to use vapor water as the product. So it's going to be the negative of the lower heating value, which is going to be equal to minus 802.4. So this is going to be entering at 25 degrees C and 1 atmosphere, which is a nice, convenient condition because that's my reference state. Question?
Will the lower heating value always be equal to the delta H reaction?
No, only for this specific example, because this is exactly stoichiometric ratio methane combustion. So if you're burning a fuel, you don't have to calculate the heat of reaction. You could just look up its delta H of combustion. And if you wanted to have vapor products versus liquid water products, you would just do the difference in the heat of vaporizations. Question?
So in order to have it be equal with like the stoichiometric ratio and everything you mentioned, you also have the water having to be a vapor at 25 degrees Celsius. Is that?
So I could do this whole process here as well and call this liquid water. In that case, I would use the higher heating value for the delta H of reaction.
But if it was vapor water that was like way hotter, you couldn't use it.
I could, but then I would just have to, when I calculated the enthalpy of the outlet, I would have included that heat of vaporization to get to my final enthalpy. Question?
So for perfectly balanced, I mean, I get that this isn't possible in real life, but like for perfectly balanced systems that have complete combustion, we can assume the lower heating value is equal to the heat of reaction.
So I misspoke. You don't actually have to have stoichiometric ratios or perfectly balanced processes. This is still the heat of reaction.
Oh,
But you would just have a different extent of reaction.
okay.
So in this case, the extent of reaction is going to be 1.
So for
But if I had excess of something or incomplete combustion, I could still use exactly this as the delta H of reaction, but I would just have a different extent of reaction. So I misspoke, yeah. So this is not only specifically for this scenario. This is going to be the case regardless. Okay. So my process is to do the energy balance now. So the energy balance is the heat is equal to 0, which is the extent of reaction times by the delta H of reaction plus the summation of the enthalpies out of the system minus the summation of the enthalpies into the system. And this is 0 because we are starting off with the molecular species at 25 degrees C in 1 atmosphere. That is our reference state. So this is where the heat of reaction method makes the problem nice and quick and easy, right? So it simplifies our algebra here. So in this scenario, we're having complete combustion. So the extent of reaction is just 1 mole. And so then we can write that minus the delta H of reaction at the standard state is equal to the summation of the enthalpies out. So it's the flow rate of the CO2 times the enthalpy of the CO2 plus the flow rate of the water multiplied by the enthalpy of the water. So we are almost done with this calculation. We just need to determine what are the enthalpies for CO2 and for water. So how would I get that? So my reference state is 25 degrees C in 1 atmosphere. So I need to get a number that I can put into my formula to work out this problem. So how do I get from my reference state to the final state? Yes? We could do C sub P delta T if we assume it's constant, which we will. But more generally, right, a delta H is equal to H final minus H initial. So we're going to start off at 25 degrees C in 1 atmosphere, which is going to be 0. So that means that our final enthalpy value that I will put into my equation is going to be equal to the delta H calculation going from the initial to the final state. In this scenario here, we're just heating it up. So heating up enthalpies, this is going to be integral from T1 to T2, C sub P dt. If we assume that the heat capacity is constant, this is going to be C sub P delta T or C sub P T2 minus T1. Okay? So in thermodynamics, we can only calculate delta H's. But the nice thing is that if we start our delta H journey at the reference state, that means that the final enthalpy value that we will put into our table is the delta H value. Okay? And so for this one, it's just changing the temperature. I actually am going to assume a constant heat capacity, which is probably a very bad assumption for this problem, but we're going to roll with it for a second. Okay? So we're going to assume constant heat capacities. Question?
So I was talking to Michael about it the other day, and he said for the class, generally, if we assume like C sub P is constant, then we won't run into much trouble. But then obviously, like in real world situations, there's a lot of times we probably shouldn't assume that.
In real world situations, you should almost never assume that if it's for like the final process design.
Okay.
For like a back of the envelope starting, sure, maybe you can get away with it.
Okay, so we're just assuming it just for the ease of class.
Yeah, just for the simplicity of this calculation, just so I can show you the equation. Because if I don't make this a simplification, the equation on the board gets very long. But using a computer, it's almost just as easy to not assume constant CCP as it is to assume. Because like if you go into the back of the book, right? If I want to know what the heat capacity of acetylene is at 75 degrees C, I still have to type in A plus B times 73 plus C times this plus D times this, right? Or I could just as easily copy those numbers into an Excel spreadsheet, and then I don't have to actually calculate anything. I can just integrate it on the computer, right? So it's almost just as easy to not assume it's a constant heat capacity. It's literally the same amount of work, because the hard part is typing the numbers of A, B, C, and D into the system, not T2 squared minus T1 squared. That's the easy part. It is, but what if I didn't give you the heat capacity and you had to look it up and you had to find a correlation? Once you look up the correlation, then it's almost just as easy to not assume a constant heat capacity. Okay. Technically, yes, it's more work, but it's like not that much more work. All right, so we're going to substitute in our delta H here, which is going to be equal to the enthalpy value that we're going to get out of this. So this is the flow rate of CO2 times the heat capacity of CO2. T2, which is going to be our outlet temperature, so I'll just call this T out, minus 25 degrees C, plus the flow rate of water, heat capacity of water, T out, minus 25 degrees C. We have one equation and one unknown, right? What is the outlet temperature given that Q is equal to 0? But I'm using exactly the same energy balance. I'm using exactly the same tools and processes. The only difference is that I am not calculating for Q based on a given T out. I'm calculating the T out based on a given Q. Now, does this have to be adiabatic? What if I said Q was minus 75 kilojoules? Would this change my formula here? A little bit. I'd have this minus 75 here, but apart from that, it's still just algebraic expression. So be comfortable manipulating these expressions anyway. I'll give you an example of where that may occur, right? Let's say we're calculating the adiabatic flame temperature, but it's not perfectly insulated burner, and you have some heat given off, and maybe you can measure the heat and estimate how much heat is being given off. Then you could throw that number into your energy balance, and you could figure out how much you're actually getting out of the process, right? So that'd be an example of that. Okay, so I'll throw up some numbers here.
Sorry, what does that say, T something minus 25?
T out minus 25, T out minus 25. So we're going from 25 degrees C, which is the reference state, to the outlet temperature, which is unknown. But given this heat of reaction, oops, let me put kilojoules per mole here. Right? So this is kilojoules per mole of the extent of reaction, which is going to work out to be just 1 because you have 1 methane. Its stoichiometric coefficient is -1, right? So this kilojoules per mole of combustion is for one batch of stuff. But in heat of combustion, we generally take this fuel as the reference for that reaction. Okay, so heat capacity for CO2 that I did the number crunching for is 33 joules per mole Kelvin. And for the water, it is 36 joules per mole Kelvin. Do I have a problem that I have my heat capacity per Kelvin, but my delta T per Celsius? Do I have a problem? No, why don't I have a problem there? The deltas are the same, right? Delta 1 degree C is the same as delta 1 Kelvin. And for some reason, you don't say degrees Kelvin, you just say Kelvin, right? So just don't embarrass yourself in the future. All right, so T out. Anyone want to venture a guess? What do we think that the outlet temperature of this is, assuming constant heat capacities, burning methane in pure oxygen? What is the temperature outlet? Okay, we have 1,000 at least. Okay, what else?
Guesses?
Yeah. 250. Okay. Back here. 900.
420.
420. Okay, funny. This is in Celsius. Does anyone want to go higher? 550.
1750.
1750. Okay. The answer. Now the problem is these heat capacities increase as the temperature goes up. So this value is an overestimate. It is 7,800 degrees Celsius. Okay. But this is burning in pure oxygen. Okay. So if I had done this calculation, but instead of pure oxygen, I had the nitrogen that came along with oxygen in the air, that number would be 2,200 degrees Celsius. And this is the adiabatic flame temperature. All right, so it is how hot that fuel will burn with no heat being removed or lost in the system. So, liquid fuels, very good, right, at providing energy. So the question, in our energy balances so far, everything is controlled by enthalpy and internal energy. We've only introduced temperature and pressure, right, to allow us to work with the energy balance. Okay? So for all of the calculations that we've done for energy balances, we've actually combined two different concepts. One is the energy balance, and that is you are an energy accountant. Do not lose energy. For the material balances, you are a mass or a mole accountant. Don't lose mass or moles. Okay? The second part of all of these calculations has been the concept of state changes. Right? So we combine the energy balance with delta H calculations, and that's how we're allowed to solve these problems. The energy balance itself doesn't have any temperature or pressure built into it. So if I'm looking at my thermocouple or I'm tapping my pressure gauge, right, that doesn't help me at all with the energy balance. I have to use state change calculations. How much does the delta H change with temperature? How much does the delta H change with phase transitions? How much does the delta H change with pressure changes? That is the second part, which is the state changes. So anytime you are doing an energy balance calculation, you need to combine the two and separate them in your brain. This is my energy balance. I need to find the enthalpy values at that certain temperature and pressure. I'm going to use state changes to get me that value. Question?
So methane is the natural gas we mostly use in our households, and adiabatic flame temperature of it is 2200 C. Why doesn't it melt first?
Oh, we don't burn it in pure oxygen. We burn it in air.
Well, no, but
it's colder.
2200 would melt steel.
This is going to be an overestimate as well because I didn't use variable heat capacities. And you're not going to have a perfectly adiabatic process as well. You're going to have a little bit excess air as well. But no, they get hot, right? So if you're ever doing, if anyone's ever done glass work, right? You're using a acetylene torch. Those get very, very hot. Their flame temperatures to melt glass and get you to manipulate it and make all of your scientific equipment. So yeah, it's hot.
Then that's just the flame, right?
That's the flame. That's the flame assuming no energy is lost. But energy is always going to be lost in a real process. Okay, so the second question is, why would I care about one fuel burning at one temperature versus another fuel burning at a different temperature? And to that, we need to talk about heat transfer. Now, has anyone here signed up for their classes? Are you registered for heat transfer in the fall? Okay, here's your introduction to heat transfer. What's the law that dictates heat transfer? Does anyone know it? Maybe you'll so if I say Fourier's law? Anyone heard of Fourier's law? Okay. In heat transfer, we will use Q, right? Just like that Q, right? Q dot. This is the rate of heat transfer. Yes.
Sorry, I don't know if there's like, okay.
Fourier. Like a Fourier transform. Fourier's law. So the rate of heat transfer, okay, for a real process, and this is true for everything, unless you get to like some really weird esoteric scenarios, but this is basically the best continuum approximation. Okay, rate of heat transfer. This is going to be in joules per meter squared per second. So how much heat is transferred across a given area in a given unit of time. This here is our heat transfer coefficient, K. This is going to be joules per meter second. This is a property of the material that you're working with. So water has a different constant versus steel versus copper. And this term, anyone know what this upside down triangle T is? Is the gradient of T. So in Cartesian coordinates, the gradient of T is equal to dt dx plus dt dy plus dt dz. So, right? So this is a gradient in 3 dimensions. So it's basically telling you what is the slope of my landscape, but we cannot visualize it because it's 3 dimensions, so we like to simplify it down to 1 or 2 dimensions so we can talk about it a little bit more clearly. Because you have a scalar value of temperature at every point in 3D space, so you cannot visualize what the gradient of that 3D space would have to be in all of those 3 dimensions, because you're adding an additional concept of the gradient. So every point in space will have a vector gradient. This is vector. This is vector calculus.
I vaguely remember.
Right? Right? So you have a vector that points to the gradient of every 3D point in space, and that vector has 3 component vectors, the x, y, and z direction. Right? The reason why we like vector calculus, and most of you probably don't like vector calculus.
And gradient is a vector, right?
Yes. Yes, gradient is a vector. So this is a vector here. The reason why we like this is because I can do all of my mathematical manipulations of my vector calculus expressions without assuming if I'm going to solve this in spherical, Cartesian, or cylindrical coordinate systems. Right? So this equation holds true regardless of the coordinate system. So that's why we like to use this obnoxious vector calculus notation, because then we can decide at the point of solution which coordinate space do I want to work in. Question?
Isn't it the double derivative of x, y, and z? Or?
No, that would be the Laplacian, I think.
Yeah.
I think I got this right. I think I got it right. I think the Laplacian, the triangle squared, that's the Laplacian. That's the second derivative.
Yeah.
So the T's in units of like Kelvin, right?
Yeah.
So those units for the gradient would be like Kelvin per meter.
Yes.
So why the final units, that's just going to end up being joules, Kelvin, meter squared per second, where the Q is just in joules.
Oh, yeah. I think I got something wrong here. I think I am missing joules per meter squared Kelvin. You're right. It's either, I think it's here. Joules per meter per second Kelvin, I think.
So T would be in Kelvin per meter?
Yeah. So this is Kelvin per meter.
Well, so I'm just so
This is not important. We're not going to be quizzed on this. I'm just sort of giving you an introduction.
But
Yeah.
for the vector gradient of T, is each one of those dt, dx, dt, dy, each one of those a vector component, or each of those is a vector itself, and adding all those vectors together to get
So this is a vector, and these are all vectors pointing in the direction of the unit, or what's it called, a basis?
So they're all vector components.
So these would all be times by the component vector for x, y, and z.
Okay.
But I'm truncating that notation. Yeah. Okay. Anyway, let's not get caught up too much, because this is not something that you're going to have to worry about for this class. And this notation is probably something that won't even be extensively covered in your undergraduate heat transfer class. This is more of a graduate transport approach, looking at the vector calculus of all of this. But anyway, let's just start and look at one dimension. Okay? So Q, let's just look at it in a one-dimensional heat diffusion scenario. Right? So the rate of heat flux is going to be equal to the temperature gradient multiplied by a heat transfer coefficient. So if we have some sort of a heat exchanger, so I'll draw a shell and tube heat exchanger. Okay, so this is going to be like your project where you need to deliver a certain amount of heat. This is going to be part 2 of the project, rather. You need to deliver a certain amount of heat to your steam reforming reactor, for example, right? And so you're going to have a heat exchanger where the chemical reaction is going to be occurring on the inside. So I need to get energy from the stream on the outlet of the heat exchanger to the inlet of the heat exchanger. So if I choose a reference point, for example, and I draw in like this, okay? So I'm going to look in, this is my x direction, going in like this. So I'm going to look at my, actually let me just draw this bigger here. My temperature versus my position x. That's a bad looking x. Okay? So I'm looking at the temperature from here going in to the center of my pipe. So if my outlet of the pipe is some sort of a flowing liquid, I'm going to have a temperature profile that kind of looks a little bit like this. This is the combination of solving fluid mechanics with the energy balance in Fourier's law. Right? So this is a partial differential equation solution. I'm going to hit the pipe wall. Inside the pipe wall, I'm going to have a linear gradient. And then on the other side, I'm going to have a curve that looks like this. Again, this is the coupled solution of the fluid mechanics plus the heat transfer. So every point in space has a particular fluid velocity, has a particular temperature, and it's conducting its heat in all 3 dimensions. Then I'm going to hit the pipe wall. Thankfully, it's not flowing, so we don't have to do the fluid mechanics. This is just a solution to the heat transfer partial differential equation, right? And it turns out it's just a nice straight line. Okay? Then I have the same problem, but on the inside of the tube, right? I have a coupled solution of the fluid mechanics and the partial differential equation of the heat transfer itself. I think Dr. Powell and Pershing. Okay? So, temperature flows from high to low, correct? Okay? So the gradient points this way. Actually, no, sorry, the gradient, my bad, the gradient points this way, mathematically, right? The slope is going this way. But the heat transfer is going the negative of the gradient, so that's why it goes from high to low. So if I need to get my reaction inside of this heat exchanger to, let's say, 900 degrees C, that means I need to have a fuel that is burning at a temperature that is greater than 900 C. Otherwise, I can't get my heat to go from high to low. Does that make sense? So we do care about the temperature in terms of the physics. So when it comes to the process engineering class that we're in right now, right, we say Q is equal to this, or we are solving for what Q needs to be removed from the process. What we need to add on to that picture once we go into the junior year and the senior year is how do we actually accomplish that Q? What temperature of fluid flowing at what flow rate would give us the correct Q to remove the overall heat transfer given the temperature difference between the 2 materials? What should the length of my tube be? What should the wall thickness of my tube be? What should the composition of that tube be? And how many tubes do I need to have to accomplish my calculation from the process engineering class that we're in right now of removing 500 megajoules of energy from that stream? That is your heat transfer course. Now we have exactly the same problem when it comes to mass transfer. So if I'm trying to perform a distillation process, how can I ensure that fluid A is going to diffuse away from fluid B to form the two separate phases. How big are those bubbles? How long does it take for a molecule to diffuse out of one bubble? The smaller the bubbles you make, the faster the mass transfer is, but the higher the pressure loss is going to be in your process, because making small bubbles and squeezing them through small constrictions is going to be difficult. Let's say I need to react, right, methane with steam to form carbon monoxide and hydrogen in the steam-reforming reaction. How quickly does that reaction take place? At what temperature and what size of a reactor is going to be the best balance for optimum productivity? If the equilibrium shifts to the right at high temperatures, that means I'm making more product, but I have to burn more fuel to get the system to a higher temperature to accomplish that objective. So everything that we've covered in this class so far is talking about, hypothetically, this is the amount of heat that we need to get in and out of the process. This is the chemical reaction that we need to take place. As soon as we transition into the junior year, you actually have to solve that problem, saying, okay, how do I actually get this reaction to occur to that completion in this size of reactor? How do I actually get my stream to be 900 degrees C? How many tubes? How thick should the walls be? If I run the process at a higher temperature, I need thicker walled tubes. Thicker walled tubes are going to have more thermal resistance. The heat transfer is going to be lower, so that means my combustion fuel needs to burn hotter in order to get the same amount of energy inside that tube. And so you see how everything is very complicated and very coupled together. And I'll double check this. I think I got the units here right. But I'm pretty sure triangle squared is the Laplacian, and that's a scalar. No, that's still a vector. But yeah, upside down triangle, almost certain that's the gradient. Okay. This is the one I'm missing. I'm pretty sure these are the units then for the heat transfer coefficient. Or this is actually the thermal conductivity. If I get this wrong, I'll let you know. Let's assume that it's correct, but I'm pretty sure that unit's right. Okay. Practice on, overview on Wednesday, midterm 3 on Friday.